Okay, let us see this other example. It says a box of weight 40 newtons is pressed on a horizontal table. Full stop. It's pulled along by a light elastic string with natural length 8 meters and modulus 56 newtons. If the acceleration of the box is 35 centimeters per second and the coefficient of friction between the box and the table is 0.5, find the length of the string after stretching it if it's pulled horizontally. So start by sketching. Of course, the other information and you put it there. So we have our horizontal table. This is going to be my horizontal table. I have a box. It has, of course, because has contact, we are going to expect reaction there. And then we are going to expect, of course, the weight. Now they are dealing that weight, so you don't need to multiply it by B because we have the weight as 949 newtons. Of course, because this is rough, we are going to expect friction this side. This is going to be equal to mu r, the reaction, that's the friction. And then we are going to be expecting this to be pulling it in that order. So we are pulling this in this direction. Of course, we are going to expect some detention that's going to pull this side. So we have this as T. Of course, because it's elastic, it means that it's going to be stretched. So we are saying maybe its natural length is stopping here. Then we say from here up to here. That's why we are going to be having our 8 meters up there. Then from here up to maybe that point is where I'm going to have a stretch distance x. So that's where they are stretching. So they want us to get this length from here up to here. That's the distance they want to get after stretch. So basically, that's what we have. In simple terms, everything we need, we have it there. Now, we are going to use the Newton's second law of motion. First of all, we start our R here, resolving. That our R is going to be equal to 9 newtons. And by now, our force, remember they gave us mu as 0.5, the coefficient of friction between the table and then the box. So, meaning my F, which is equal to mu R, my F is going to be, first of all, this is 0.5 times 9. So my F here is going to be here I'm getting 24.5 newtons. So this is the frictional force that I have there. Okay, now let us see what happens if we remember this one is accelerating. It's accelerating in that direction. So that's where acceleration is occurring. But they give us the acceleration as 35 centimeters per second. Means that now we first convert this to meters per second. So our acceleration is going to be 35 over 100. Maybe every centimeter is having 100. And this one becomes meters per second. So this is going to be 0.35 meters per second. So now our acceleration is also in meters. Okay. So after doing the acceleration, remember that the acceleration is occurring in that direction. So you see that now using Newton's second law. Using the second law, you know that, what does it say? The resultant force is equal to the mass times the acceleration. Now, our acceleration is that it's going in that direction, and you say the direction of acceleration is in the direction of the force. So what is pulling it in that direction? I think you can see we need also the mass. So our mass, remember, our mass times V is equal to the weight. So our mass M times 9.8 is going to be equal to our weight, which is 49. And the divide there is that our mass is going to be 5 kilograms. If you divide it that side. So we have the mass. So meaning my F R equal to 2 ma means that our acceleration is in this direction. So what is pulling it in this direction? I think we see that we have T, but it's something opposing the friction. So minus F equaling to the mass, which is now 5, times the acceleration, which is 0.35. And so you see that this one, our T now, is going to be now 3.0.35 then plus F. This F which is 24.5. So our T is, so in simple terms, we want to get this X, and the only way we had to get this X is by getting the tension, and if we have the tension, we have the modulus of elasticity, we had the natural length, so that's why we had to get tension first. Now the tension in this string, so there we are going to be having there we have 26.25 newtons. So the length I want, I need first of all the length from here up to here, I need this X, and that's extension or that straight or that extended distance. The only is only related with the formula of from Hooke's law. Okay, so if I have that, now it's that my from T equaling to lambda X over L. I have the natural length there. I think we can see that our L is 8 meters, comma. Do we have lambda? Yes, our lambda is what? They gave us 56 newtons. And we have the tension. So substituting there, we have 26.25 equaling to 56x over the natural length, which is 8. So 26.25 is equaling 7x. And if we divide there, our we get 3.75 meters. So meaning that now the length will be, we are not going to have 8 plus x. We add this plus this, which will give us 8 plus 3.75, which will give us 11.75 meters. Sorry, these are meters. So this is the length after stretching this, and you are pulling it in that direction. So that's it, members. I wish you well. Basically, you had to see, to get the length, you needed to get x. To get x, this is now the extension. We needed to use the Hooke's law formula. Then the Hooke's law requires us to get tension. The tension in the spring, we had to first use the Newton's second law. After that, remember, we are having the force opposing friction, putting it there, and everything is in order like that. So, that's it. Don't forget to subscribe to the channel. I wish you well.